Uh, well, this may be a short class, or almost certainly will be, depending on um, what y'all have in the way of homework questions. All right, so this is the very last material that will be on test 2, and then um, on Monday I'll go over the practice test 2 and answer any questions you may have about that. Um, now, last time, okay, last time I showed you the method of characteristics for solving a linear first order PDE in T and X. So now we're going to look at the quasi-linear case, where the coefficients A, B, and C are allowed to depend on the solution U. And oh, okay, I see we've had a couple more show up. So thank you for getting here shortly before I started jumping into the notes. Okay. So the method of characteristics still applies, but certainly the fact that it's no longer linear equation can make things more difficult, but also lead to very interesting behavior of a solution. And we're actually going to focus on an application that's a truly real world application, and that is uh, traffic flow. All right. So to model traffic flow, um, our solution U of xt represents at any particular point on the road, at any time t, U would be the density of cars at that location at that time. As a measure of traffic congestion. Um, so to derive a PDE that models the flow of traffic and how the density evolves over time and space, we have this conservation equation. So just as a heat equation was derived from a conservation equation, we have the same kind of principle guiding the derivation of this PDE. Um, so, um, so this conservation equation, both sides represent in different ways the change in the number of cars within a particular segment of a highway. So it's this interval AB. Um, because so du dt is going to be the change in density with respect to time, but then we're integrating that over with respect to x over an entire segment. So during that's so within that segment we have that's a total change with respect to time of a number of cars in that segment. Now, on the right side, f of xt is the flux, which refers to cars per minute passing the point x. So what we have here is cars passing a point A. So these are cars entering the segment, and then we're subtracting out cars that are leaving the segment. So what we have here in total, by subtracting these two fluxes, this is cars per minute. So if we're using t as you having a unit of minutes, so this also represents the time rate of change of a number of cars within the entire segment AB. So okay, so I should make that clear here. Change with respect to time in the total number of cars within this segment. So the left side focuses arrives at this quantity by considering what's going on in the interior of a segment, this considers what's going on at the boundaries of a segment. So now this difference of f values can be expressed as an integral of the derivative of f with respect to x. So I can write it this way, because if I take this definite integral, I would get f, and then plug in the values of a and b and subtract. The minus is here because we have the lower limit a first. So now I rearrange this equation because now everything is the integral. Oops, that should be x, not t. So now everything is the integral over ab with respect to x, so I can move this everything over to one side. So now I have this integral of this quantity being 0. But now, using the same idea as we did to finish off a derivation of a heat equation, the segment AB is arbitrary. So because the integral of this quantity over any segment is 0, that means that this quantity must be 0 everywhere, not just its integral. So now we end up with this PDE, ut plus fx is equal to 0. So this is a standard form for writing a conservation equation. So U refers to like a density or concentration of something, and then F is the flux of that same quantity. So it's basically it's flow rate at any particular point. So there are a lot of PDEs that have this general form for some flux function F. So now we're going to try to solve this conservation equation. So on the entire real number line, so we have no boundary conditions to worry about. We do have an initial condition, initial data phi. Now, I'm going to use a chain rule to rewrite df dx as df du dx. So now that lets me rewrite the PDE in this form, where I have g, some function g of u, so that's df du. So now I have ut and ux in this PDE. And the reason why I've done this is it puts the PDE in a form where I'm able to use method of characteristics. Because you recall, in method of characteristics, we had a coefficient times ux plus a coefficient times ut plus additional term is equal to 0. And then I applied method of characteristics to that. So now I can do that with this problem. So when I apply method of characteristics, so remember the coefficient of ux. So if I go to this form of PDE, the coefficient of coefficient of du dx is my right hand side for my x ODE, and then the coefficient of ut, which is just 1 in this case, that is the right hand side of my ODE for t. And since the initial condition is specified on the x-axis, where t is 0, then the initial value for t is 0, and then the initial value for x is this variable tau that marks positions along the x-axis. And so from before, S is a parameter for each characteristic curve, so it describes movement along each individual characteristic curve. This is indicating where on the x-axis a given characteristic curve begins. So now, if I go back to my PDE, I had ut plus g of u ux, but this is the same as ut ts, which is 1, plus ux xs, which is g, but this, by the multivariable chain rule, is du ds. So now I just have this ODE, du ds is equal to 0. So that drastically simplifies the original PDE to this ODE. And then the initial value comes straight from the initial data. And since tau is equal to x on the x-axis, it's 5 tau. So any questions up to this point as to where these equations came from? Now, fortunately, this ODE is quite simple to solve. Okay. Okay. Now, so what we have here is since u does not change with respect to s, in terms of s, u is just a constant, this constant. So, sorry, I just realized that I have a typo here. Okay. So u is just equal to 5 tau. So that lets me, so by solving this right away, because it's the simplest equation to solve, here I have u of tau s, but by solving this, keep in mind that u doesn't change with s. U of tau s is simply u of tau 0. So this du ds being 0 allows me to change this to this. So I can just set s equals 0. Because what this is saying is the value of s doesn't matter as far as it doesn't influence u at all. But u of tau 0 I have here from initial condition. That's 5 tau. So I can fill that in. And then I have my initial condition from before. Now, the nice thing is, because dx ds is equal to this function that does not depend on s in any way, I can go ahead and integrate both sides with respect to s. So I would get x on the left side, and then this, because this is a constant as far as s is concerned, I'll just multiply this by s. And then when I integrate, I do get a constant of integration, my plus c, but that would be equal to tau, because you have to make sure that when I set s equal to 0, this term goes away. Tau is what has to be left. So this is the solution of this initial value problem that came from here. Here too, I can integrate both sides of this because the right-hand side does not depend on t at all. I integrate both sides, I get t is equal to s plus a constant of integration, but because of this initial condition, that constant of integration will be 0, so t just turns out to be s. So so you can verify directly that this x and this t satisfy both ODEs and the corresponding initial conditions. So now all three of these equations for x, t, and u have been solved. Any questions about how those solutions were arrived at? And this is what I mentioned earlier, that u of tau s just turns out to be 5 tau because u doesn't depend on s. So we actually have our solution as a function of tau and s, but we need a solution that's in terms of x and t. So, so what I can do is I can go back to this equation, and I can solve for tau. So, so if I rearrange this, tau is equal to x minus this term. But phi of tau is u, and s is t. So that's how I get this, x minus g of ut. So rearranging this and expressing in terms of, and keeping in mind that u is phi of tau gives me this expression here. So now I have a solution u of x as a function of x and t. The problem is it's implicitly defined because we have u on both sides of the equation. I do not have an explicit formula u of xt equals something where I could just plug in an x and t and get a value of u. So that's kind of unfortunate that if I want to know a value of a solution at a particular xt, I have to solve this generally nonlinear equation. I'm going to have to use some iterative method to do that. But I want to show you how you would verify that this really is a solution, even though it's implicit. Or wait. Okay. Actually, I need to check something here before I continue in the textbook. Okay. Lesson 28, problems 1 and 5. I want to make sure I'm not accidentally giving away the answer to a homework problem. Come on. Lesson 28. Oh, sorry. I can't do that. I had something in my notes here about verifying that this is a solution, and that would give away the answer to one of the homework problems from this lesson. But what it would amount to is making use of a chain rule, because if you're taking derivative of both sides of this equation in respect to t or x, then you'd have to use a chain rule and take appropriate derivatives of this with respect to t or x. And then, so you're taking like derivative with respect to t to get ut, you're going to end up with ut on both sides of the equation. And then you can rearrange to solve for ut, and similar with ux, to confirm that it's a solution. But yeah, unfortunately, in most cases, based on the function phi, that we can't get an explicit formula for our solution. But we're not entirely out of luck here. We still can understand how the solution behaves by looking at the characteristic curves. Because the way these first order equations work is that you have your initial data is propagating along these curves. And that's what this equation right here is saying, that as time moves forward, because s equals t, you have a characteristic curve that's starting at a certain point on the x-axis, so the point tau 0. And as time moves forward, this equation defines, or these two equations define a characteristic curve. And that value of a solution at phi at that particular point on the x-axis will propagate along the curve that is parameterized by these equations. So So, okay. So more concretely, suppose we have a curve that begins at a particular point x naught on the x-axis at time 0. So you can think of x naught as being tau in these equations here. So a characteristic curve satisfies this equation so a point xt on the curve satisfies this. And so you can think of this as being actually this equation right here, all that just comes from rearranging this, where tau is x naught and s is equal to t. So rearranging that gives us this. As long as this value of your coefficient g is non-zero, otherwise the characteristic curve would just be a vertical line. So along this curve, the solution is equal to your initial data phi at that point x naught. So this curve can be going wherever in the xt plane, and the solution along that curve will be equal to this. So that value is being carried forward from the x-axis into the xt plane as t increases. And you can actually think of this as, because really, because of the particular form of PDE we have, this characteristic curve is actually a line. So you can think of t as being like playing a role of a y coordinate. We're looking at the xt plane, and this 1 over g, that is the slope of the line. Okay. So what we have is from the x-axis, we have all of these lines emanating, and the slope is determined by the value of g at the initial data. Now, there's a fundamental difference in behavior between first order PDE of this kind that are linear versus nonlinear. So what's interesting about the nonlinear case that could never happen for linear PDE is these characteristic curves, it's possible they might intersect. So like, for example, what could happen is here this characteristic curve is a line that emanates from some point x naught on the x-axis. And suppose that you have a line that's behaving like this, but then further down, you have another characteristic curve that has a much steeper slope. So it's increasing much faster. So you have this curve here, this curve here. Eventually, they could cross. So the problem is, each of these characteristic curves is carrying some value of phi along it. So if you have two different phi values traveling along these characteristic curves and the curves intersect, then at that intersection point, well, which value of phi is it? You have a conflict. It's like the solution is becoming multi-valued. Another way of looking at it is it causes a discontinuity in the solution because the solution is trying to assume two different values at the same point in the xt plane. So when that conflict occurs, that leads to a jump discontinuity in the solution. That's called a shock. So this is something that can occur for these first order nonlinear PDEs, but not in the linear case, because it can be shown that those characteristic curves would not cross each other in that case. So how does the solution behave once a shock occurs? So the discontinuity is going to continue propagating with this speed that comes from the value of your flux function at the two conflicting values. So this is your value on the left side of a jump. Here's a value on the right side. So So this difference quotient gives you a slope, and that's going to be the speed at which the shock will propagate. Um, so so when you have a conflict, you have this you basically have a wave that is moving at a constant speed uh, after that point. Now, I can actually explain what this means in a real life setting, and it's quite unusual to be able to observe the solution of a PDE in a real life situation, but I actually was able to do that. Um, so 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 what happened was, this is from a few years ago. I was taking a road trip and I was driving through the Houston area, and you've been there, but there could be a lot of traffic. So on this occasion, there was a fair amount of traffic. It was pretty heavy, but we were still able to move along pretty quickly. Like traffic was going around 65. Um, but then traffic was getting heavier and heavier because it was getting towards the end of a workday. More people are getting on the freeways. So at some point, the freeways got too clogged, and so we were forced to slow down. And so we're all slowing down. And the thing is, there's no there's no particular disruption. There's no accident or anything like that happening. It just, the density got too great, and we all slowed down. And we all slowed down like to a crawl, like nearly to a stop, which of course is quite annoying. And then after a little bit, we all started moving again, and at a good speed, like close to 65 again, and we were all moving like in lockstep. It's not like, for example, when you are, stopped at a red light, let's say you're several cars back, the light turns green, and you have to wait quite a while before you're able to move. And that's actually a sign of hyperbolic PDE, such as this one, that you have what's called a finite speed of propagation. And that's why there's that lag in time before you're able to go. But in this case, we were all moving in unison at a uniform speed after that initial slowdown. That's this phenomenon in action. So when we got slowed down in the first place, that's when a shock occurred. So characteristic curves crossing because of a sudden increase in the density of cars on the road. And then we continue moving past the shock at this uniform speed after that. So it was quite eye-opening when I got to experience that. It's like, wow, this is exactly what the mathematics predicts. And even though it's a PDE of a fairly simple form that would only take into account certain effects and neglect others, it's so remarkably accurate in terms of how a solution behaves versus what you observe in reality. And when I lived in California, I'd experienced this quite often where we're chugging along pretty good, and then all of a sudden there'd be this abrupt slowdown for no identifiable reason, and then we'd all get moving again in unison. So, um, so these models, if carefully designed, really do capture that behavior, and that's why we make these models to understand what's going on, and that can lead to designing roads, interchanges, and so forth to try to try to improve traffic flow if possible. And when changes are proposed, then instead of going ahead and building it and seeing what happens, we can try to simulate what would happen by solving these kind of equations and in that kind of a system to get an idea if it seems to actually help or not. And that's one of the key applications of PDEs, is to try to simulate these things before they're tried out for real at great effort and expense. Okay. All right. So questions about what you've seen here, or about any homework problems?
Dr. Lambers,
Yeah.
I have a question.
Okay.
It's lesson 24, number 2.
Okay. All right, I'm gonna unshare and reshare to. Oh. Okay.
So it follows from number 1, which we solved earlier, and then after doing that, my final result was different from the back of the book. I just wanted to make sure it wasn't a mistake in the book. I don't know, maybe it was me, but
Okay. All right. So what's supposed to happen? Okay, with this initial data, it's supposed to be t times v. Okay. Okay. Sorry, the background noises.
Sorry, I can mute.
Yeah, please do. Okay. So what you can do? So the idea is, if you go ahead and solve this problem, where so now x is here is the initial data, and then and in that case, because it's a Cauchy problem, you can use D'Alembert solution formula, and then take a derivative out of respect to t. Okay, so now if I take a look, now I have not had anyone ask me questions about this problem before, so I would not know off the top of my head.
My answer also doesn't match with the book's answer.
Okay. All right. So what would happen is, okay, so if you're taking, yeah, because normally what you would do is you'd have this as your starting point, where this would be x and c would be 1, and then you would take the derivative of that with respect to t. Shiley, how did your answer differ from this one?
I don't have the T. I just have X.
Me too.
You only had okay.
Yeah.
Yeah, because what would happen is okay. And actually that does make sense because okay. Oh, sorry. I forgot you could see that. Okay, where am I? Lesson. Oh, I got to go ways away back. Certainly this kind of problem would have a unique solution. Sorry, it always takes forever to scroll for this damn thing. Sorry. Okay, lesson 24. Okay. Because if a solution being x, that would certainly satisfy the wave equation because you get 0 on both sides, and then it'll be x. Yeah, x times t is definitely not the solution of this problem. So both of you got that? It's just plain x?
Yeah, and I think several more just said they did too.
Okay, then x it is.
Thank you.
Okay. Any other question? Okay. So between now and Monday, now that everything has been covered for test 2, be sure to take a look at the practice test and see if everything makes sense and how those problems are worked out, so that you'll be ready to do a real thing. But keeping in mind, there will be certain small changes in the particulars of a problem. So be sure to pay attention to how the problems are worded in a practice versus a real one when you get it. So I don't want to have needless point loss like there was last time. So, okay, so I'll stop recording at this point, but anyone's welcome to stick around if you still want to ask questions.